Hey everyone, welcome to The Explainer. Today, we're jumping right in and setting the stage for a hyper-focused dive into the absolute fundamentals of mechanical stability. We're going to look at a concept that perfectly captures the whole butterfly effect in massive construction projects. It's this wild situation where a tiny, almost microscopic detail completely dictates the success or failure of a colossal feat of engineering.
I want you to just picture something for a second. Imagine a towering 100-meter chemical distillation column. Or think about a massive 1,000-ton piece of rotating equipment just operating at extreme speeds. How does that towering monolith stay perfectly upright during a literal typhoon? How on earth does a monstrously heavy pump not just vibrate itself to pieces under all that stress? Well, the secret isn't actually in the massive steel structure itself. It literally lies in the earth right below it.
Okay, let's dive into this. Way before any of that heavy machinery ever even arrives at the site, we have the concrete foundation. But notice the mystery here. Look at these metal rods sticking out of the concrete, all carefully wrapped up in these protective orange and blue covers. Those right there? Those are the anchor bolts. They literally just wait patiently in the mud and the dust, long before the star of the show, the equipment, makes its grand entrance.
Now, I'm going to plant a little seed of conflict right here. What do you think happens if just one of those bolts is, say, a single centimeter too short? I mean, it just sounds like a rounding error, right? No big deal. Well, actually, that tiny miscalculation can lead to an absolute multi-million-dollar disaster, completely derailing the entire project schedule. And to really grasp why that is, we've got to transition from the macro view of a sprawling industrial plant right down to the micro view of just one single anchor bolt.
Section 1. Anchor bolts, the plant's bones.
So these bolts are essentially the literal skeleton holding the equipment to the earth. Without them, the plant honestly has no bones. Think about it like this. If you've ever had a washing machine at home that wasn't perfectly leveled, you know exactly how violently that thing can shake, right? It feels like it's going to tear your laundry room apart. Now, take that exact same physics and scale it up to a massive industrial level. Without properly secured anchor bolts locking the equipment down into a solid concrete foundation, the immense kinetic energy of a chemical plant would quite literally rip the facility apart. It's crazy. So we know these structural bones are vital, but we really need to focus on one hyper-specific characteristic of this bolt.
Section 2. What is projection?
This is a term that plant engineers absolutely obsess over, and trust me, for good reason. In standard engineering vocab, projection is defined as the specific length of the anchor bolt that remains exposed above the concrete foundation after the concrete has been poured and fully set. It's that exact, precise measurement from the surface of the gray concrete all the way up to the very top tip of the threaded bolt.
There's actually a saying in the industry that perfectly captures the gravity of this measurement. A machine is only as secure as the calculated length of its projection. And you know this exposed length? It isn't just a random guess. It's definitely not something the civil team just eyeballs on site and says, yeah, looks good enough. It is a highly calculated mathematical absolute, and it has to be rigorously verified in what's formally known as the Section 2.2.3 Anchor Bolt Projection Check. This happens long before any equipment is ever lowered into place by a crane. So how exactly do engineers arrive at this magic number? Let's break down the math behind the check.
Section 3. Perfect projection calculation method.
It's actually a really fascinating yet incredibly simple puzzle to solve once you know the pieces. The perfect projection length is basically just the stacked sum of 5 crucial physical elements. Okay, first, you need space for the grout thickness. Second, space for the shim plate thickness. Third, you've got to add the thickness of the heavy equipment base plate itself. Fourth, you account for the thickness of the washer and the fastening nut. And then finally, step 5, you have to add enough length for exactly 2 to 3 exposed threads sticking out past the nut for ultimate safety.
Section 4. The secret of hidden space.
Now, if you think back to those first 2 steps for a second, you might be a little confused. I mean, why on earth are we calculating space for grout and shims? Why is there a gap between the solid concrete and the heavy machine in the first place? Shouldn't the steel just sit completely flush against the foundation? Well, here's a fundamental truth of construction. Concrete is rarely perfectly flat at a microscopic level. Because of that, plant engineering actually requires a hidden layer. We use precision steel shim plates to achieve absolute flawless leveling of the machinery, and then we fill that remaining gap with high-strength epoxy grout to create a perfectly solid, unyielding base. Both of these completely necessary layers chew up a pretty significant portion of the bolt's overall projection length. And this brilliantly illustrates exactly what we're talking about. When we look at a completed installation, that calculated projection is doing its exact job. The steel base plate is resting securely right in place, the heavy-duty nuts are clamped down incredibly tight, and right there at the top, those 2 to 3 exposed threads are sticking out. That right there is the visual confirmation that the mathematical formula worked flawlessly in the real world. But what happens when the math goes wrong? What happens when the civil construction team pours that foundation and the projection is just off?
Section 5. Fatal consequences of failure.
Let's finally answer that mystery we posed at the very beginning of the explainer. It really all comes down to 2 potential errors. The bolt is either too long or it's too short. If the projection is too long, okay, it's definitely annoying. It might get in the way of piping or somebody's walking path, but hey, it's fixable. You can literally just cut the excess steel down. But if the bolt is too short, oh man, that is a catastrophic failure. You literally cannot safely fasten the nut. And last time I checked, you can't just stretch hardened steel.
So, the crucial point is this. A short bolt means you absolutely cannot secure the equipment. It introduces severe, potentially deadly vibration risks. And fixing it? Well, that requires either incredibly expensive, highly specialized welding extensions that will absolutely ruin your project timeline, or, worst of all, the complete demolition and repouring of that entire concrete foundation. This is exactly why the Section 2.2.3 projection check is an utterly unforgiving, non-negotiable step. You have to get this right before millions of dollars of equipment are suspended in the air.
It really is a fascinating journey, going from the macro way down to the micro and then zooming back out to the macro again. Rigorous attention to these tiny details, like calculating the exact length of just 3 tiny exposed metal threads, is the invisible shield that ensures the mechanical safety, the structural integrity, and honestly, the financial timeline of the entire megaplant project.
Which brings us to a final, honestly staggering thought. If the length of a single, humble anchor bolt requires this level of obsessive mathematical precision and physical inspection, just imagine the sheer scale of the math, the engineering, and the coordination required to build the entire rest of the plant. I mean, it truly is a marvel of human achievement. Thank you so much for joining me on this explainer, and hey, keep questioning the engineering all around you.